Okay, we have 18 holes in the golf course, and each windmill has a number of blades. I see. Okay, so this is going to be another interactive problem. The number of knights and the number of gophers. And okay. So how many gophers can there be? There can be 1 million gophers and only have a week. Whew. Okay. Well, so each night we get quite a bit of information, right? We can just sum up the, like suppose that we set all of the holes to 18 blades, then we know the number of gophers mod 18. Seems pretty good. And in fact, we can maybe just use Chinese remainder, because if we get some primes. Okay, so what are some primes? Those are all the primes less than 18. So how many of them are there? 1, 2, 3, 4, 5, 6, 7. Hey, how about that? That's not good enough. Okay, that lets us figure out up to 500,000 gophers, but there's actually 1 million gophers. We can just do 4 instead of 2 though, right? Yeah. Okay. Great. So this gives us the sums modulo all of these numbers, and then we just need to put it together with the power of the Chinese remainder theorem. So let's find out how the Chinese remainder theorem works, shall we? Yeah, it's a very good theory. Existence. General case. Just do the general case, yes. They may be computed by the extended Euclidean algorithm. It would be nice if I could use 2. I'd only had to deal with primes. But with prime powers, I mean, I could just be lazy and only fit in 8 at the end. Systematic search. Yeah, that is fair enough. Let's just do that. That seems easier than 4D math. Okay. we're going to get n, or we're going to get t, and then we're going to get n and m. Okay. Yeah, seems good enough for now. Let's see. Okay. Yeah. What are the equators supposed to be? We're supposed to output 18 numbers, and we're supposed to get back 18 numbers, right? Yes. Okay, let's get their testing tool. think that means it's correct. Okay, well, let's see. Okay, so while that's judging, what is the idea here? So if we set all the blades to the same number, then we know that the total number of rotations must be the total number of Gophers. Well, obviously, that's always true. And so if we take the total number of rotations, like we can't see if one of the blades might have rotated all the way around, and we can't notice. But if we set them all to the same number, then they're all going to always be rotated. However much we missed, it's always going to be a multiple of that number, right? So we at least know the number of Gophers modulo that number, and if the Chinese remainder theorem says that if we have a bunch of modular equations and all the moduli are co-prime, then there's a unique solution up to the product of the moduli. So if we can find some co-prime, 7 co-prime moduli, each less than or equal to 18, that multiply to more than 10 to the 6, then we're good. So the natural way to do that is try to pick the moduli as high as possible, so as pick prime powers. So conveniently, there are exactly 7 primes less than 18, or less than or equal to 18. 18 is not prime, so it doesn't matter. 2, 3, 5, 7, 11, 13, and 17. The product of those is only 500,000, though, and we need a million. But we can just take the powers of some of those primes. So instead of 2, we can use 8, and we're already up to 2 million, and that's enough. Instead of 3, we could have used 9 as well. So that would have brought us an extra factor of 3 if we needed it. So once we have these modular equations, how do we solve them? So there is actually a fast way to reconstruct the solution, but in this case, we know that the number of Gophers is between 1 and a million, so we can just try all the numbers between 1 and a million. It's very fast to try a number, right? You just need to check if the 7 moduli work out. So yeah, that's the last problem, and that's the whole contest. So I will check back in after the contest to see how I did.